So in this video, we will see about graph traversal. So in this graph traversal, we need to visit all the vertices in the given graph. So graph traversal algorithms, there are two types of algorithms, BFS and DFS. So BFS means breadth first search, DFS means depth first search. So the difference between DFS and BFS is how the adjacent vertices of each vertex is visited. We will see these two algorithms one by one with one example. Just take this given graph. So this given graph is a undirected graph. Now I will explain how BFS works for this particular. So in it, we already know in a tree traversal, pre-order, in-order, post-order. So in the tree traversal, the traversal should start from the root node. But in graph, there is no such any starting point. So we can select, we can start our traversal from any vertex in the graph. So in this example, I will take vertex A. We will start traversal from vertex A. So in the BFS, so I will explain this example with state space tree. In the BFS, first I start that vertex A and then I make that vertex A as visitor. So I will use one list, visited list. So first I take A as visitor. So and then next I need to explore all the adjacent vertex of A. So adjacent vertex are which are directly connected with A. So in this example, there are two adjacent vertices, B and C. So in BFS, once the adjacent vertices are explored, all the adjacent vertices would be included in the visited list. So both B and C are now included in the visited list. So next, now we have to unexplored vertices in our state space tree, B and C. So here the first unvisited vertex is B. I am going to do the same process. Now explore the adjacent vertices of B. So adjacent vertices of B here, A, C and D. So the vertices which are directly connected to B are A, C and D. So in these three vertices, A and C already included and already visited. So no need to explore that two vertices again. So this B has only one unvisited adjacent vertex T. So I add that in the state space tree and that T should be included in the visited list. So now the next node, unvisited, unexplored node in our state space tree is C. So explore this C. C has adjacent vertices of C are A, B, D, and E. So in this four vertices, already A, B, D are visited. So no need to include these vertices again in our state space tree. So only one vertex which is left is E. So add that vertex in our state space tree. So and then include it in the visited list. So now all five vertexes are visited. So this is the working principle of BFS. So we can So for this, in order to explain this, I use state space P. So start from any vertex, include that vertex in the visitor list, and expand that vertex. That means I include all the adjacent vertexes which are not unvisited already in the state space tree, as well as add it into the visited list and repeat it for each and every unvisited or unexplored nodes in the state space tree until all the vertexes in the graph has been visited. So now, how it can be implemented? So it can be implemented by using the BFS can be implemented by using the data structure queue. So how a queue can be used to implement this? So for actual implementation, we use one. So queue is first in, first out. Okay. So one queue. So first I'm going to add A in the queue, starting vertex. So then I also use another list, a list or array anything. So that is visited list. So this is a visited list. So I add one element A. Initially, one vertex is added. Then we need to dequeue. Once a new the vertex is added, we need to do a enqueue dequeue process. First A is enqueue. Then I'm performing dequeue. So now A is dequeued from the queue and this A is added in the list. This is visited list. So now after the A is dequeued, we need to include all the adjacent vertexes of A which are unvisited, which are not in the visited list. So now the unvisited and the adjacent vertexes of A are B and C. So now next I need to do that NQ. Sorry, now B and C are enqueued, which are the adjacent and unvisited adjacent vertexes of A. Now I perform DQ. So DQ means which is the first element in the queue. So now B is the first element. So I A already DQ'd. So DQ this B and add this B to the visited list. So now we need to include all the adjacent vertexes of B which are unvisited. So adjacent vertexes of B are A, C, D. So now C is already in the queue, A is already visited. So we need to add only D. So once this NQ process is completed, again we go for DQ. So the first element in the queue is C. So perform TQ and then C in the visited list. Now we need to include all the elements, all the adjacent vertex of C into the queue. So adjacent vertex of C are A, B, D, and E. In this, A, B are already visited and D is already included in the queue. So only we need to include E. So after this NQ process, now perform DQ, the first element in that Q is D. So include this D in the visited list. Now we need to add all the adjacent vertex of D. So adjacent vertex of D are B, C, yeah, and E. So already B and C are visited and E is already included in the. So now need to include NQ any vertex into the Q. So next we need to perform DQ operation from that Q. So only one element, that is E. So now that E into the visited list. So the simple process is we have one queue. Initially the queue is empty and I NQ one element into that queue. Then I DQ that element, all the adjacent vertex of DQ'd element into the queue, and that adjacent vertexes should not be visited, already should not be visited. That means they are not present in the visited list and they are already not in the queue also. And we need to repeat this process until queue is empty. So now I will explain, I will give you the implementation of this BFS. This is the pseudocode of BFS. So BFS, it start from one start node. So initially create one empty queue and one empty list V. So first NQ that start node into that queue. So in this example, first initially A is NQ'd. So then while Q is not empty, initially Q contains only element A, so it is not empty. So select new Q, one element from Q and store it one pointer current. So now A will be NQ and current pointer is A. Then that current pointer should be added into that list B. So here once A is DQ, that A is added into that list. Then for all neighbors N of current, now current is A and all the neighbors of A, that are B and C. For all neighbors, we need to check whether that neighbor N is not in Q or V. So we need to check B and C. Both B and C are not at the state. Both B and C will not be in both Q and V. So we need to add both B and C into the Q. NQ. Both B and C will be NQ. Then again, we need to repeat the same process until the Q become empty. So this is the actual implementation of BFS. For depth first search, the data structure used is a stack. It can be implemented using stack. So the traversal start from one initial vertex, a start vertex. First, that start vertex is should be pushed into the stack. For example, if we start from our traversal from using vertex A, so A is now pushed into the stack. So while the stack is not empty, until the stack contains at least one element, we need to repeat in process. So first we need to pop the top element from the current stack. So current stack, the top element is A. So we need to pop it out and add it in the visited list. Then all the neighbors of the top element, the main element which is popped on, all the neighbors should be pushed into the stack. So for the neighbors of A is B and C. So for the consistent hours, we can push these adjacent vertex in the reverse order. So first push C, so and then push B. So next we need to pop the top element from the current stack. Now the stack contains two elements C and B. So the top element is B. So B should be popped out and it should be added into the visited list. Then the neighbors of B should be pushed into the stack. So neighbors of the B are A. A is already in the visited list. C. C is already included in the stack. Then D. So D is not in both stack and list. So D should be pushed into the stack. So now the current stack, the top element is D. So pop that T and include that T in the visited list, and the neighbors, unvisited neighbors of D should be pushed. So D has neighbor B. B is already visited. C is already included in the list, and E. So E is not visited and not is in the list. So next we need to push E into the stack. Then the top element of the current stack is C. So pop that E and then include that E in the visited list. So now the neighbors, unvisited neighbors of the top element, the top out element E should be put into the stack. So neighbors are C and D. So D is already visited and C is in the stack already. So no need to include any new neighbor. Then now the stack is not empty. So again we need to do that operation. Now the top element is C because at this stage the stack only contains C. So already A, B, D, E are popped out. So only C is left in the stack. So we need to pop it and include it in the list. Now stock becomes empty. So we need to stop this traversal here. Now the order of traversal, BFS traversal is A, B, D, E, C. So this is depth first search. Now the pseudocode for this depth first search. This is the pseudocode for DFS. First, we create one empty stack S and one empty list V. So the list V is for a visited list. Initially, the start element is pushed into the stack, and until the stock is not empty, then each time the top element, the current top element, the stack is pushed, and that top element is appended into the visited list V. Once the top element is appended, we check all the neighbors of the top element. And the neighbors which are not visited, so for all neighbors of current. So current is nothing but the element which is popped out, a top element. For all neighbors of that vertex current, if the neighbor is not visited already, then that neighbor is pushed into the stack yes. Then the same process is repeated until the stack is become empty. This is the implementation of DFS. Both BFS and DFS are graph traversal algorithms, and BFS can be implemented using data structure 2, and DFS can be implemented by using data structure stack. Thank you.